that a number of the lattices that you see or a number of the posets that you see, actually they deal with subsets. So your operations that you have are intersections and unions. And in those cases, your meet, it does correspond to intersecting the two subsets, if those are your first points. So in terms of what they are, the definition of a meet is the greatest lower bound. It's probably, what that means right here with the blue, this is the formal symbolic definition, but honestly it's probably easiest to see it from a picture. And there's two situations that you can have. If the two elements, A and B that are in your poset, are actually comparable, in other words, there is a specific edge between the two of them, the meet is the element of those two elements that's below the other one. Okay? If, however, the two elements are not comparable, in other words, there's no direct edge connecting these two guys, the meet is the greatest lower bound. Lower part refers to it's got to be below your two elements, and greatest means you've gone up as high as you possibly can to be below your two elements. So these yellow bits right here, those are the highlighted vertices in the poset. That would be your meet. Now the join is exactly the opposite. This guy is the least upper bound. So if you have two elements, if they are comparable, in other words, if you have an edge between them, the least upper bound is the one that's above the other one, whichever one is above the other one. Okay? If, however, the two elements are not comparable, in other words, they don't have an edge between them, the least upper bound is some vertex in your poset that is above both of them. In other words, from each of these two guys, you can travel up a path to get to it, but it's also the first one they would both get to. Okay? It's the first time they join together, if you will. Okay? These were sort of descriptors of how you got to them inside the poset. And then we ended last time that said, hey, if you have to have for a lattice, every pair of elements has to have their meets and joins, what that means is automatically a lattice always has its greatest, or as your book calls it, maximum element, as well as its least, or as your book calls it, your minimum element. And those are all perfectly fine words. Okay? Now, let us look at some examples. So suppose we have the following examples, and I've actually got 5 examples here prepped up. And for these guys, didn't actually give you what the underlying structure of the poset is or what the specific relation is. All I gave here were the Hasse diagrams associated with your poset. And what we want to do is we want to check to see, hey, are any of these guys lattices or not? And I'm just going to give you a heads up. Some of them are lattices, and some of them are not lattices. Okay? Now, the first guy that we have, and let me make sure that I'm actually drawing here in black. I'm not even sure if I'm drawing right now. Nope. So this first guy is somebody that we've talked about before. It looks like it just looks like a single line, a single path, if you will. This guy has that special buzzword of a chain. And let me scroll down here. We might be able to get, nope, I can't. I was hoping we could get the definitions of both a meet and a join, but we didn't. So this guy had a name. It was a chain. I do not care if you remember that name or not, but it's nice to recognize it. Now over here to the side, just to make sure that we can actually see it while we're working on the problem, let me go ahead and do the little picture dealing with your meet and your join. So I remember the meet was the one that was the greatest lower bound, because I almost said the wrong thing. So if we are looking at the greatest lower bound, we are looking at this guy. And the join was the least upper bound. So that's just so we can see it while we're working on the questions. All right, so if we look at a chain, the question is, if you pick any pair of elements in this chain, do those pair of elements always have a meet and a join? So if you pick an arbitrary pair, what's an arbitrary pair of elements that you guys like? And I'll highlight them here in the poset, or in the Hasse diagram technically. Anybody got a pair of elements here that you guys would like me to look at? I'm not seeing any guesses come in, so I'll just pick two. How about A and maybe C? Okay. Now notice if we pick any other pair of elements, maybe we pick A and B, they're also stacked, just like this. Maybe we pick A and D, they also would be stacked. Maybe B and C, B and D, C and D, any pair of elements you picked, they're going to look like a subchain. And a subchain is what? It looks like the full chain that we have in this Hasse diagram, but potentially smaller as long as we don't pick the elements A and D, which would look like the full chain. Okay? So a subchain like subset. Okay? Now, what that means is those two pair of elements are a representative pair, and if we get a meet and a join for looking at elements A and C, that means any other pair of elements would also have both a meet as well as a join. So if we look at elements A and C, what do you guys think? Who would be the meet of elements A and C? Yep, the lowest one there would be the meet. Anybody got a guess who would be the join of elements A and C? Yep, perfect. That's one of the nice things about if you have chains or subchains, if you want to be precise here, is the highest element in that little chain or subchain is going to be your join, and the lowest element in that chain or the subchain is going to be your meet. That's actually really, really critical because that's something that we'll actually deal with in the larger graphs as well. I shouldn't say graphs. My other class that I'm teaching this summer is graphs, and we have a huge overlap in these two sections. Brain needs to be more focused. I need more coffee today. Anyway, in these other Hasse diagrams, which are actually a type of graph, sort of, kind of, not really. In these other Hasse diagrams, while not everything that you can get is a chain, you definitely have subchains or baby chains involved, or sub-posets, if you will. It's not really what they're called. In here, like for example, if we had picked B and D, and we'll talk about this when we move to this next Hasse diagram, that forms a little baby chain right there. Well, one of the things we're about to get is a result that deals with chains. Okay? So if you have a chain here, and notice we've got a chain right here, and we even have the subchain that we were looking on with A to C when we compared those guys, it turns out a chain is always, what do you guys think? Is this guy a lattice? Do all the meets and joins exist? So this is going to be our answer. Chains are or are not lattices. Yep, they are lattices. And they are actually one of the building blocks that we use to determine whether other types of posets, which are not chains, are also lattices too. So they're a pretty big deal. So if you ever see a chain or some part of another poset that is a chain, you know automatically it has all of its meets and all of its joins. So what happens is when we move to these other posets, so let's look at this second poset here that's sort of same row but over a little bit to the right. This one looks like a square on point, and we actually saw this one previously. This guy actually, if you want its name, is a Boolean Algebra. This is B2. Okay? Now, let's check to see if this guy is a lattice or not. Now, what do? You have to check every pair of elements inside of the Hasse diagram and see if, or inside the poset, and see if for each of those pairs of elements you have a meet and a join. Now, there's a bunch of different pairs of elements that you could pick. You could pick A and D, but notice if you pick elements A and D, which are your greatest and your least elements, they represent actually two different chains, A through C up to D, or A through B up to D. And notice, so that's a little chain, and what do we know? Chain has, oh, this was just the name of it. In terms of B2 here, this one here that looks like a little square, it actually has the official name of B2. Now, a way to figure out if it's Boolean is if it looks like either a square or a three-dimensional cube. Those are the guys that are the Boolean ones. And we can, when we get done with looking at these examples of lattices, I can go back and show you the specific deal with the Boolean algebras again. Right, so we want to look at every pair of elements here and make sure we have a meet and a join. So A and D, the meet would be A, the join would be D. If we looked at somebody that was just connected by one of the edges right here, if we were in a digraph, an arrow, but for us, just looks like a line segment. So A and C, well, that's just another baby chain. A would be the meet, C would be the join. We could look at A and B, again, another baby chain. A would be the meet, B would be the join. We could look at B and D or C and D. Both of those two cases, the top one would be the join and the bottom one would be the meet. Now, notice what this tells you. This tells you, since so many of those guys that look like little baby chains, since we already know chains have all of their meets and joins, that's something that if you're trying to be lazy or do a shortcut, you don't check anybody or you don't have to really fixate on any pair of elements that form a chain because you know they already have their meets and joins. So instead of fixating on any of those elements, I'm going to go and tag the only two elements in this particular poset that don't form a little baby chain. In other words, two elements that are not comparable. Okay? So in this particular case, B and C are not comparable elements. Why? Because there's no edge between them, because there's no path to get from B to C or vice versa. Okay? Now, if we're looking at the two elements B and C, could we actually figure out the meet and the join of B and C? And I'm going to put the work to the side for this one. Anybody have a guess what the meet would be for this one? And remember, the meet was the greatest lower bound. Now, your only possibilities for answers are the elements of the poset, so A, B, C, or D, or does not exist. That's also a possibility. So what do you guys think? What might be the meet or here? Your greatest lower bound. In this one, it actually does exist, so you'll be able to find it. If it doesn't exist, that would be one of the times when we don't have a lattice. So that'll be one of our future ones. B. Nope, it's not going to be B. So this one's going to be different than a chain. Your meet and your join actually are not going to be the elements B or C. So any guesses which one the meet would be? Notice I've eliminated it down to two choices for you, either A or D. Correct. So the meet here would be A. Now let's see why it would be A, because this one does look different than the other ones. So there's A. This is the guy that's going to be your meet. Ah, that was trying to be a B. Huh? So what do? We see, hey, there's no edge between these guys. If there's no edge between these guys for the meet, you look down below your two elements. So we look below B, we look below C, and the first time those two paths going down, so the opposite way of what we should be going, meet up or get to the same exact element, that's the time when you define your meet. So your meet is the first or the highest element below your B and your C that both B and C came from, if you want to follow the arrows in the correct direction, even though we have like invisible arrows. Notice what we're doing. This is the situation right here. That is actually the most common situation. Your meet is defined as the first time, if you look below your two elements, you are able to follow your little edges down to have a shared or common element, if you will. Hopefully that kind of made sense. So this is actually one of the most common things. These two guys are like the representatives of the two things you see in terms of your Hasse diagrams. So let's finish this off. Anybody have a guess what the join of B and C might be? Yep, so it would be D, and you actually use the same sort of logical thinking. So with the join, what you do is if the two elements are not comparable, so that means you have no edges that actually travel between these two guys. There's no way to start at B and get over to C. In this case, you would look up from both of them, and it's the first time you get to a element in common. Now, sometimes if the Hasse diagram is much bigger, you're going to have several elements in your poset that you could reach from B and C. So the join is the first one you get to. It's the least upper bound, so the lowest common element above them. Okay. So these two guys right here are the two quintessential examples of the two different cases that you can see inside of a lattice. B2 here, so this one, it actually turns out that you can say this in general. All of your Boolean algebras are lattices. But specifically, that one is a lattice. So part of speech is a lattice. There we go. Okay. So these are the two classic examples. These two would be ones in terms of, so B2 is just the name of this guy. That's all it is. I don't care if you remember that part or not. Okay. What we'll do at the end is when we finish this example here, I'll go back and show you the picture of the standard little Boolean algebras. And this was the Boolean algebra when you had 4 little vertices. Okay. But remind me at the end, we'll go down and we'll look at that again. But again, if you don't 100% remember this particular name, it'd be awesome if you could, but probably not the biggest deal in the world. All right, so let us look at the next examples. The first two examples here were both lattices. They are actually both really, really common lattices. Now, next two examples also are Hasse diagrams of some posets. And we want to ask the exact same question, and that exact same question is, are they actually Hasse diagrams of lattices? So let me move down our little cheat sheet of what a meet and a join is over there to the side, and let us now look at these new two guys. Oh, actually, the third one came up too. So these are the last 3 Hasse diagrams of posets we want to check to see if they're lattices or not. So this one here that looks kind of like a Y shape, it's got 4 vertices or 4 elements in the building set, A through D here. Notice if you're trying to check if you want a lattice, what do? You check each pair of vertices and see if you actually have see if they both have a meet and a join. Okay. So if you pick a pair of vertices like A and B, notice right there, that totally builds a little baby chain. We know chains have both a meet and a join. If you pick A and C, that's again a little baby chain, so that there also would have a meet and a join. The join would be the top element, and the meet would be the bottom one. If you look at A to D, that also forms a little chain. The join would be at the top, the meet would be at the bottom. Now, if you started at B, you could do B and C, you could be B and D. Both of those are little one-edge chains, so your meet would be B and your join would be whichever the top of the chain was. Okay? Now, that gets us to all of our pairs of elements except for one, and the only one that we haven't checked yet is C and D. So if we look at elements C and D, if we want to find the meet of elements C and D, anybody have a guess what it would be? And notice again, what I do, I picked that pair of elements that didn't have a path between them. Okay. Yep, and you guys are totally right. This is B. So on purpose, picked a pair of elements here that were not comparable. Okay. They didn't have some way to go from C to D. The only way you could go to C to D is we had to go back the wrong way on an arrow. That's not allowed. Okay. So you guys are 100% correct on the meet. Excuse me. Next, we want to find the join. Anybody have a guess what the join is? It's supposed to be pointy. What do you guys think? What's the join of this, of C and D? Correct. So this is a situation where you do not have a join. Now, anybody have a guess why you don't have a join? Don't overthink it. Why did you guys think the join didn't exist, for those of you who thought that? Yeah, exactly. There's nothing above C and D. So notice this is a situation that we've looked at before. Actually, we might have looked at that exact poset before when we were looking at our greatest elements and our maximal elements and our minimal elements and our least elements. This is a situation where you have two maximal elements, and then what happens, you had no greatest element. Well, it turns out if you have more than one maximal element, you're going to get, if you pick a pair of elements where they're both maximal elements, the join will not exist. Same thing happens on the bottom. Well, not in this example, but if you had a different Hasse diagram of a poset, if there was more than one minimal element, you wouldn't have a meet between those elements, okay? But yeah, so this one here, you get it does not exist for the join of elements C and D. Now, conclusion, can this poset, or the Hasse diagram of the poset this represents, could that poset be a lattice? What do you guys think? Is it a lattice or is it not a lattice? Got to fill in the blank there of is a lattice or is not a lattice. Correct. So this one here would be not a lattice, and it would be not a lattice because you've got that does not exist. So as soon as you get a does not exist for at least one, and it doesn't matter if there's more than one, but at least one of your meets and joins across one of your pairs of elements, that means it can't be a lattice because a lattice says all of your meets and joins have to exist. Okay, so that would be one situation of how you could, not be a lattice. Okay, and that, if all we're asked is this poset a lattice or not, we're done. We actually could have gone directly to those two elements to start with and not even have to worry about bothering to check any others because we had a failure. All right, so let us look at this next one right here. Okay. But before I move on to that one, any questions about that Hasse diagram that kind of looks like a Y-shaped? All right. Well, in that case, let us move on to this next guy. So this next guy looks really similar to some of the Hasse diagrams that we've actually created in the past that had that were like those D with a subscript. Okay. So just as a heads up, because I know this is probably a question in at least some of your guys' minds. If you're asked to deal with some of these different posets, especially the ones that have the names, like for example the D and then the subscript with some number that says, hey, you take all the positive divisors of whatever that number was, and then our relation is blank as a factor of the other element, I will actually give you that description, that definition of what that symbol is. So I'll tell you what your building set is, and I'll tell you what your relation is, okay? Same deal with the Boolean algebras. In those cases, I'll tell you, hey, this is the underlining set, this is the relation, this is the symbol. If you remember what the symbols of the B with the subscript, but the D with the subscript is, it'll be quicker for you to get through some of the poset questions that you may see. But in terms of do you have to remember it, no, I'll write all that stuff out for you guys, okay? It'll be up near the top of the question. Now, that being said, this isn't really one of those guys. So if we look at this guy, it has now 5 little vertices, so A through E. If we want to know, is this guy a lattice or not, what do we already know? We know if we pick any pair, they better have a meet and a join. And we know a lot of these guys are going to be chains. So like AD, that's little baby chain. A to E, that's a little baby chain. Or the other way is also a little baby chain. A to B, little baby chain. A to C, little baby chain. A to E, well, we already talked about that one. We could also do B to C or B to E are little baby chains. C to E is a little baby chain, and D to E is a little baby chain. So the only way to start finding places where maybe you don't have a meet or a join is if you look at your not comparable vertices or not comparable elements. So for example, if you pick B and D, I am already regretting picking B and D because they're fun to say next to each other. What do we do? On purpose, I picked two guys here that don't have a direct path between them. From B, you can get up to C or E, but you can't get over to D. From D, you can get up to E, but you can't get over to the other side. So if we look at B and D, what do you guys think? Do we have the meet in the join of B and D? So the join of B and D would be who? Who do you guys think the join would be? Oh, as I'm doing the wrong thing here. It would be either C or E. It would be one of them. And remember what the join is. It's the least upper bound. So you have to go up from both of them to be able to get to the first element in common. So from B, you go up to C. But from D, you can't get over to C, so you have to go one further up. So it actually turns out to be E for the join here. Now, in terms of the meet, yes, but you've got them reversed. So in terms of the meet being the greatest lower bound, this one you go down, and yep, it would totally be A. Careful, it's super duper easy to do. I actually kept reversing meets and joins with both the word and the symbol, and not because I didn't know what they were. The symbols look so incredibly the same. I kept reversing them in my head. I didn't stop reversing them until grad school. I mean, it took a while. I don't even know why, but it definitely took a while. One of the things that I found that helps some people is these little guys, the caret and the V shape. You can think of it as pointing towards your element. So like on the meet, this is like an arrow pointing up to your element A, up to your element B. With the join, it's like an arrowhead pointing down to your element A, down to your element B. If that helps, go for it. If it doesn't help, don't try to remember that. Because sometimes if you use little ways of memory tricks and they don't work for your brain, it just makes you more confused. Okay? But that was one way that I found has helped people, is these little carets, think of them as like arrowheads, and they're pointing towards the two elements that you care about. That only really helps once you know where the meet and the join are, so it's sort of backwards, but Either way, we've got what? We've got both a meet and a join for both of these two guys. It's a little bit different in the join because we had to go up a little bit higher on the sides with the B. Now, notice though, in this case, we actually have a second pair of not comparable vertices, specifically vertices C and D, or elements C and D. So if we look at the meet and join of C and D, and let's actually do these guys in the order of a meet and a join. Anybody have a guess the meet on C and D? And remember, meet is the greatest lower bound, so you're looking down. Yep, this one you have to go all the way down to A. D goes down directly to A, but C you have to travel down a couple more vertices. Now, anybody have a guess on what the join is of C and D? It would be E, perfect. And these are the only two pair of elements in this particular poset that are not comparable. In other words, they don't form a little baby chain. Now, once we've got a meet and join for both of these two pairs, what does that mean? That tells us that this guy is what? Is a lattice or is not a lattice? And notice I'm only checking the ones explicitly and writing them down where the two elements do not form a little baby chain. You could actually do it for all of the elements. Ooh, let me answer that last question about A and E being incomparable, but yes, the answer in total here is we actually are going to be a lattice in this case. So if you looked at, and let me color code this something else, how about that really ugly purple color? Whoever thought that was an awesome color for highlighting was not correct. So suppose we take A and E, which in this case are your maximum and minimum elements, or maximal and minimal elements. They're actually both. Anybody have a guess what the meat would be of A and E? So I'm going to throw that to you guys. And remember, the meat is the greatest lower bound. So you're looking below. It would be A. So these two guys actually form a little baby chain, either length 2 if you go through D, or length 3 if you go on the other side. That's okay. It happens. Okay. Now, anybody have a guess what the join would be of these two? It would be all the way up to E. So this guy turns out to be, even though they're not right next to each other, there's not a single edge connecting those two vertices, they actually do form a longer chain inside of the poset, which means the same thing happens here as our very, very first example, which we'll be able to get a meet and a join. The join, the higher of the two elements, and the meet, the lower of the two elements. So we're still good. No. Okay, am I back? Can you guys hear me now? Or it's just you? Okay. Well, nobody else said anything, so it could have been them too. Hopefully you guys can hear me again. Okay, awesome. Whew. Okay, so that takes us to the last of these 5 examples. So the last example here actually has 6 vertices or 6 elements in the poset. It actually looks really, really, really similar to the last one, except there's internal edges right here. Okay. Now, in terms of looking at this guy, notice what do we want to do? Same thing as before. We want to make sure that all pairs of elements inside of the poset do have a meet and a join. So just like before, there's lots of pairs of elements here that have that form little baby chains. So we're going to ignore those guys in part because of time issue. Okay. So like A and B forms a little baby chain. A and D forms a little baby chain. If you watch where my cursor is here, let me blow up here because I know some of you are on cell phones and I'm sure it's much harder to see. So A and D form a little chain. A all the way to F forms a little chain. A to E forms a chain one of 2 ways. A to C forms a little chain. So if you start at A and go anywhere else, it forms a little chain. Now, if you start at B, B to D forms a chain. B to E forms a chain. B to F forms a chain. You can't get between B and C, so there's an incomparable guy. So let's actually grab that one because we know that's an incomparable guy. Okay. Now, we also have C to D, that's the baby chain. C to F, that's the baby chain. C to A, we already looked at. C to E is the baby chain. C to F is the baby chain. B to C, we already know is incomparable. And if we go up here to D, D to F is a baby chain. E to F is a baby chain. But D and E are what? They are also incomparable. So we've got 2 pairs of guys that are incomparable. So we've got 2 pairs of elements that we need to worry about. I'm not going to worry about anti-chains with you guys outside of the homework. So that's not something I would ask you about either on the test or an example that we're going to talk about right now. Now, in terms of looking at these little elements, let's look at B and C first. So if we look at the meet and the join of C, and let me move our little cheat sheet here over so we can see it. So anybody have a guess what the meet is for this particular, for the elements B and C while I'm moving our cheat sheet over so we can see it better? So any guesses what the meet is between B and C or of B and C? Yep, look down, greatest lower bound, so it's the one below. So the meet would be A, no worries there. Now, anybody have a guess what the join is of B and C? And remember, the join is the least upper bound, so you're looking up. Ooh, it's not F. F is an upper bound, so it's one that they both get to, but it's not the least upper bound. So least needs to be closest to your elements. There you go. Now, the question mark is definitely good. So here what we have is what? If we go up from B and C, they both immediately go up to the element D, but they also immediately go up to the element E. So I definitely should have written that below the little arrow. So let's move that, because why? You can't have two answers for your meet or your join. You've got to pick one of them. So what should be our answer? Any guesses? What should be our answer for our join of B and C? This one here is probably the trickiest question of all of them we've seen so far. Is there anything in our definition of least upper bound that tells us D or E is a better element to pick? And the answer to that is no, which means if you have two possibilities for your answer, that is another way of saying this: does not exist. Now, what do we know happens when we get a does not exist? It means we can immediately answer the question of whether this guy is a lattice or not. Is this particular Hasse diagram of some poset, is the poset behind this Hasse diagram a lattice or not? What do you guys think? It is not a lattice, exactly. Now, if we decide to keep going, and you don't have to at this point, because as soon as you get it does not exist, not a lattice, you're done. But if you actually did want to look at the guys highlighted in blue here, so elements D and E, it turns out the same sort of thing happens. Their join does exist and it's F, but in terms of their meet, notice their meet could be either B or C. And since that one could be either B or C, this is another case when you get a does not exist right here. Okay, so this crisscross format right here is actually something that if you had that sort of crisscross formation inside of your Hasse diagram or your poset, that's something that you can't have with a lattice. Okay. But that's the crash course in what a lattice is. I promised you guys that I would show you the Boolean algebras, so let me do that before we get done. But that's the crash course in lattices. I shared with you guys a video in the announcement that I sent out fairly late last night that actually has more examples than what we got to today. So if you want some more examples on lattices, I'll hook that into Canvas so you can find it pretty easily. But let me show you the crash course in the Boolean algebras because it's at the end right here. So these are the first little baby Boolean algebras. The official definition of your Boolean algebra is you have some power set. And so all of these subsets, remember a power set is just all of the subsets of some other set. So your power set of the set 1 through n, ordered by set inclusion. So somebody's related to somebody else if it's a subset of the other guy. It turns out the smallest ones are these guys. They look like squares. So a single vertex, a single edge, you don't normally see those guys too much. But this one's pretty common, at least at our level. Of B2, it looks like a square. And this one here looks like a cube. That one would be B3. Okay. Now, are there other ones? Yes, definitely. And one of the defining features of these guys, these Boolean algebra, is the fact that they have 2 to the n vertices. So that's one of the ways that when you were asking, how could I recognize that that other guy was a Boolean algebra? In part because I know what the little ones look like, but also because we had a power of 2 number of vertices. But that's it. That's all I've got for you guys. There's tons more that we can do in the area of discrete math, but we were just a survey course, so got you the highlights of hopefully the stuff that you guys will need in the future. But that is it for both today and for our course. So I'll hang out for a little bit if you guys have questions, but that is